All right, here goes your exponential functions and sequences review. Now, I'm going to flip to each slide, and I'm going to give you about 5 seconds to see the problems and pause them to try and work them on your own. Then I'm going to go ahead and resume the video and play them as I work through them so that you can see if you're doing the right process or wrong process. So here we go. First up, parts of exponential functions. Alright, so parts of exponential functions. As we go through this, it asks us to identify the initial value, which we know is our a. It asks us to find our growth or decay factor, which we know is our b. And then also identify it as growth or decay. So first things first, we have to remember that we're using the function y equals a times b to the x. So it's just a matter of identifying where we're at in the equation. So y equals 6 times 2/3 raised to the x. Well, 6 is in spot of the a, so that must be my initial value. 2/3 is in place of the b, so that must be my growth or decay rate. And since that b value is between 0 and 1, that means that this graph is going to be decay. Now, of course, we can graph it on our calculators and look at the graph itself, but just looking at our b value should tell us all we need to know. So we go over to the next one. Y equals 3 times 5 raised to the x. Well, 3 is in place of my a, 5 is in place of my b, so my initial value has to be 3. My growth or decay rate is 5, and since that b value of 5 is greater than 1, we're going to say that this graph represents growth. Now going down, we read number 2, it says, Ken has decided to raise rabbits, but has been warned that the number of rabbits he will have will double every month. So that double every month sounds important. So I'm going to go ahead and highlight it. Ken started out with 65 rabbits. His started value sounds important as well. Now it's asking us to write a function that represents the situation after x months. So we know that this x has to come into play. All right, so we're going to start off with f of x equals, I'm going to start with my initial value, which in this case was my 65 rabbits because it says I started with it. And it doubles every month, so that's my b. Now, if we think doubles, we should be thinking times 2. So I'm just going to multiply that by 2 and raise it to the x power. There's my equation. Your next set of problems is exponential growth and decay functions. On these, remember that we're going to use the function f of x equals a times 1 plus or minus r raised to the t. And really, instead of f of x, it should say a of t equals. So go ahead and try and work those. All right, so as you work through these, suppose the population of deer in a state is 1,500. So it's going to start at 1,500 and is growing by 2% each year. All right, so when I write my equation, I know that I'm going to have a of t equals 1,500 times 1. In this case, since it's growing, we're going to say plus, and we have to write that 2% as a decimal, so 0.02 raised to the t. And in this case, it says that our t is going to be 4 years. So 1,500 times 1 plus 0.02 raised to the 4. And our estimated population should be around 1,623 deer. Moving on to the next one, a boat costs $83.50 and decreases in value by 12% each year. How much will it be worth after 5 years? So again, we know that we're going to start with a of t equals, our starting value is going to be $8,350. And since it decreases, we're going to say 1 minus, and 12% as a decimal is 0.12, raised to the t. So then we take 8350 times 1 minus 0.12 And our t is going to be our 5 years, so to the 5th. And the estimated cost of the boat, or the value of the boat, is going to be approximately $4,406. And last but not least, we have our population of 40 crickets that doubles in size every month. Now that's important, every month part, and you'll see why here in a second. So it gives us the function we're going to use. F of x equals 40 times 2 raised to the x. But notice how it says after 3 years. Well, if this says every month and this says after 3 years, we have to determine how many months are in 3 years. So that's simply 12 months in each year, so times 3 years, and that gives us 36. So 36 is going to be our x value. And so I get 40 times 2 raised to the 36th. And if you hate crickets, you're really going to hate this answer. The estimated population of crickets will be 2,748,779,069,000 crickets. For the next set of problems, all we're going to need to do is really graph and compare to our possible answer choices. So go ahead and give this one a few seconds. And your answer you should get is B. And then we're going to go ahead and look at the next question. Give yourself a few seconds. And the answer choice you should get here should be A. The next set is going to be exponential real-world problems. So what we need to do is we need to take everything we know about exponentials, exponential regression, and everything, and apply it to a real-world situation. So go ahead and pause it, give yourself a few seconds to work out this one, and then see how your answers compare. So for the sake of time, I went ahead and worked through this problem so you could check your work. Number 8 asks us to write an exponential model, so we just use exponential regression. Our x values are L1, our y values are L2, and we should get the equation f of x equals 198.67 times 0.87 raised to the x. We then use that equation to approximate the temperature of the water after 6 intervals. That 6 is going to be an L1, so an x value. So we simply plug it in for our exponent and we get 86.15. The domain, in this case, since it's a real-world situation, is not all real numbers. Instead, we have to look at our minimum number of intervals, which is 0. And we can have infinite intervals going forward, so x is greater than or equal to 0, so there's a restriction in place. Our range, we still have an asymptote at y equals 0, so our range would be y is greater than 0. Now look at number 11 real quick. So our y-intercept, if we recall, is still just our initial value, or our a sub 0. All right, so our initial value in this case, when x is 0, is going to be 210. So that 210 is our y-intercept, and it represents the initial temperature of the water. Now go ahead and look at these sequences for a second. Identify them as arithmetic or geometric, and see if you can find the common difference or common ratio as well. I'm not asking you to write the equation on these problems. Alright, so we can go ahead and check our answers. The first term is just subtracting 0.5 each time, so it's arithmetic, and our D, our common difference, is negative 0.5. Our second sequence, we multiply by 3 each time, so it's geometric, and our R equals 3. And then the last term is a little difficult, but we're multiplying by 1/25th, so it's geometric, and the R equals 1/25. And the last ones are going to be writing the sequence formula. So we're still doing the same thing we just did, except now we're going to actually write the formula with it. All right, so arithmetic sequence tells us exactly how we're going to write it, and geometric sequence tells us how we're going to write it. So go ahead and try and write those real quick before I post the answers. All right, so here are your final answers. So we remember arithmetic sequence is a sub n equals a sub 1 plus n minus 1 times d. So our a sub 1 is simply 3 because that was our initial value. Our d, our common difference, is 8 because we're adding 8 each time. So our answer is a sub n equals 3 plus 8 times n minus 1 since we still don't know what n is. For geometric sequences, we get a sub n equals a sub 1 times r raised to the n minus 1. A sub 1, again, is just the first term in our sequence, so it's 49. We're multiplying by 1/7 each time. And so we get our equation a sub n equals 49 times 1/7 raised to the n minus 1. Thanks, and good luck tomorrow.